Okay, we're back. Part 2 of Lecture 20. This is going to be a short one. And we're going to talk about the superposition principle, which we're going to use to solve the base excitation problem. In addition, it's a tool we'll have useful to us throughout the entire course, and very important concept you'll be using throughout your careers, actually. So, before I go on, the last video got cut off just a little bit at the end. I think my phone went off or something. I couldn't figure out how to splice the new video in. So you didn't miss anything. There were like maybe 10 seconds remaining, and I'll kind of reiterate those points in part 3 of the lecture when we solve the base excitation problem. But what I want to go over right now is just a mathematical concept that's really, really important. And this is called superposition, and it only applies when the differential equation is linear. And that's one of the reasons why linear differential equations are so much easier to deal with than nonlinear ones. Okay, so just sort of come across as a math lecture, but it basically looks like this. And we're talking about the particular solutions of differential equations because as we know, with the type of differential equations we're dealing with, the homogeneous solutions are going to decay away, and what's left in steady state is just the particular solution. So the superposition principle goes like this. Okay, basically, if you have a differential equation that looks like ax double dot plus bx dot plus cx equals f1 of t. So not talking m's, k's, and c's here, but just any constants a, b, and c. Okay? And this is a forcing function. And if you can show that if you can find a particular solution to this one, call it xp1 of t, satisfies that differential equation, and then you have same differential equation with a same differential equation on the left hand side, but with a different forcing function f2 of t, and so now you have and xp of 2 satisfies that one. So if you can find a particular solution to this, and you can find a particular solution to that, then if you have a combination of the forcing functions acting, this is not, sorry, 1, then the sum of the particular solutions to the two of these will be the particular solution to that. Okay? So then xp1 plus xp2 satisfies, gotta make it small, satisfies this. Okay, and it's a real easy proof. If you want to see the proof, there's a handout that will be up on Moodle, because I have a handout. By the way, there's a handout that accompanies this entire lecture. You know, the same handout, the same not just the handouts, but the lecture notes to the lecture will also be up on Moodle. And there's a handout that looks like this. Okay, so there it is. You know. There's what I wrote, but then there's the proof to it. It's a very simple proof. But when you realize, when you go through that proof, you basically just add these two differential equations to get this one. Okay? All right? And so And so the way we're going to use this is that, so basically, if you're given a differential equation in this form, two forcing functions, then what you can do, and it only works when this is linear, okay, these are linear with constant coefficients, but for any linear differential equation, superposition will work. And if you have a sum of two forcing functions, then what you can do is, block out one of the forcing functions and find the particular solution to just when f of 1t is active and f of 2 is not there. And then find a second particular solution for when f1 is blocked out but f2 is still there. And then your total particular solution is just the sum of those two. Okay? Very, very simple concept. Only works when it's linear, but it's super, super useful. So for example, if we go back to the forced mass, the forced mass fixed base problem, now we could solve a problem where instead of the forcing function being a simple harmonic, it can be the sum of two harmonics at two different frequencies. And we can just solve one, get a harmonic. We can just solve the other, get a harmonic, and then the total solution is the sum of the two. Okay, that's it for part 2. I'll be back with part 3 where we will solve the base excitation problem.